Hey everybody, in this video we're going to cover how to find the equation of a tangent line and normal line to a specific function with a worked example. Let's jump in. Okay, so here's the problem. Go ahead, pause the video, and see if you can figure this one out. So here are the answers. Now, if you already understand how to get these, feel free to skip the video, but if you're not sure how we got these, stick around and then we'll explain how we got them. So to get started, let's just focus on the tangent line. We'll figure out the normal line afterwards. We can get one of them, it's going to be a lot easier to get the other. So let's just worry about the tangent line first. So the tangent line, let me just say this. We're not trying to just find the slope of the tangent line. We already know how to do that. We're trying to find the equation of the entire tangent line. Now, it's useful to think about what type of equation we're actually dealing with. So a tangent line, you can think of it as its own equation, separate from the equation that it's a tangent to. But the question is, what type of function or equation is a tangent line? And the answer is kind of in the name if you think about it. So pause the video maybe and think about what type of function or what type of equation a tangent line really is. Now, if you've thought about it, hopefully it's clear that it is a linear equation, or in other words, a line equation, a straight line, like y equals mx plus b. The tangent, and you can see the name is actually in the name itself, or the word line appears in the name itself, tangent line. It's not a tangent curve, it's a tangent line, a straight line. So if you think about it, there are generally two types of equations that we use for tangent lines. One is, or for any line, I should say, one is slope-intercept form. And these names are pretty appropriate. So slope-intercept form, remember that's y equals mx plus b, where m is the slope and b is the y-intercept. So in other words, if you know the slope of the curve and you know the coordinate of the y-intercept, remember the y-intercept is just a specific point. It's the point where the curve, or the line in this case, goes through the y-axis. If you know both of those, then you can figure out the equation that tells you every value on the tangent line or on the line in general. But that's actually going to be pretty restrictive if you think about it, because we'll be able to find the slope, but it'll be a lot trickier to find the exact coordinate of the slope of the y-intercept. So what we would rather do is actually use the other form, point slope. This is the same type of thing, and again, these are named appropriately. We still need the slope with this form, but now we can just use any point. It doesn't need to be the y-intercept specifically. It can be any point. So this one is y minus y0 equals m times x minus x0. So as long as we have the coordinates of any point on the line, x0 comma y0, then we will be able to figure that out. So that's kind of our goal. And if we can figure those out, so if we can figure out the slope of the tangent line and a specific point on the tangent line, we can just plug those into here, and that will be the equation of the tangent line. So that's what we're trying to do. Now, how do we find that? Let's start with the slope. Hopefully, you already know how to find the slope of a tangent line. Remember, the slope of a tangent line at every single x value is given by the derivative of the function that it's tangent to. So if this is our function, and we want to find the slope of the tangent line, we should basically just take the derivative of that. So if I do f prime of x, that'll be what? 3x squared minus 4x minus 4. And then if I want to find the slope of the tangent line at a specific point here, x equals -1, then I can just plug in x equals -1 to that. So I'll leave some room later, but yeah, basically if I just plug in -1 here, think about what I get. I get 3 times -1 squared minus 4 times -1 minus 4. What is this? So if I get 3, if I make some room, if I get 3 times 1 minus, or plus 4, so minus 4 times -1, that'll end up being plus 4, minus 4, those cancel. So long story short, the slope of the tangent line is equal to 3. And that's, yeah, so that's the value of the derivative of this at -1, and that is the slope. The other thing that we're looking for, remember, is a specific point on the tangent line. So now let's think about this. If we have a tangent line to a curve, what point on the original curve, ideally, is guaranteed to be on the tangent line as well? The answer is the point of tangency. The point of tangency, remember, if we have a curve, just to give the idea, if you have some curve like this, the point of tangency is literally the one spot where the tangent line intersects the curve that is tangent to. Now, again, it could accidentally intersect at other spots. So, like, for example, if this is a curve, it would also accidentally intersect down here, but it's only guaranteed to intersect at one spot, the point of tangency. What is the point of tangency here? It's literally the point we're trying to find the tangent line at. So here, for example, they give us the x-coordinate of the point of tangency. So we already know x0. So we already know that x0 is equal to just -1 because they told us. All we need to figure out is y0. How can we do that? How can we figure out the y-coordinate of the point of tangency if we already know the x-coordinate? Basically, we can just plug in the x-coordinate to the original function, not the derivative of the function like we did down here. That tells us what the slope is. We're trying to find the y-coordinate right now, which means we just plug it into the original function. So if I do that, if I just plug in -1 to the original function, let's see where that takes us. I'm just blindly plugging in. It's always safest to just plug in with parentheses and then work through everything later. So here, -1 cubed, that'll be -1. It's like -2 times +1. We'll deal with that later. -4 times -1 will be +4. So think about what we have. We have -1 minus 2. That's -3 plus 4 equals 1. So there you go. We know that x of 0, we already knew that. And now we just figured out that y of 0 equals 1. So at this point, we have all the information we need. So if we take point slope form, and we kind of plug in everything that we just figured out, the slope at that point and the x and y coordinates at that point, let's see what we get. We get y minus +1 equals 3 times x minus -1. And if we simplify this down, hopefully it makes sense, y minus 1 equals 3 times x plus 1, which will be 3 times x plus 3. And then finally, if we simplify this, just by adding 1 to both sides, we get y equals 3x plus 4. So there you go. This must be the equation of the tangent line at x equals -1 to this curve. So that's half the battle. Now, what do we do? Remember this, if I simplify this, so this is kind of the tangent line, remember? I'm actually going to separate things like this just to keep it easy. Remember, let me put it this way. So that's the tangent line. Now, what is the normal line? So if we have, conceptually, what is the normal line? If this is the tangent line, what is the normal line at a certain point? Can I draw that well? Maybe like that. The normal line is really, it's kind of like the same idea, except it is perpendicular to the tangent line. Let me put it that way. That's probably the best way to understand it. So that is the normal line. The normal line's, in my opinion, a lot less useful than the tangent line, but it does have some uses, like in physics. Now, anyway, the normal line, and that's kind of the key, the normal line is perpendicular to the tangent line, but it goes through the same point. That's kind of the hint. What would that mean? Well, it basically means that x0 and y0 stay the same, but m changes. Specifically, m is going to be the negative reciprocal. So what I can do here, I can literally take this spot and I can keep everything the same, except I can change that to its negative reciprocal. So what's its negative reciprocal? That'll be -1/3. Because remember, this is an algebra idea. Negative reciprocals are basically, in order for two lines to be perpendicular, their slopes have to be the negative reciprocal to one another. And then I'll have y minus -1, which is really x plus 1. Or sorry, x minus -1, which is really x plus 1. So there you go. Once you find the tangent line, you really just go to point slope form, keep the same x and y coordinate, but just take the negative reciprocal of the slope. That'll give you the normal line. So this is the equation for the normal line, and we can simplify this down a little bit more. So what will this be? -1/3 x minus 1/3. And then if I add 1 to both sides, what is -1/3 plus 1? Think about it like -1/3 plus 3/3 equals 2/3. So you get, long story short, y equals -1/3 x plus 2/3. And there you go. That is the equation of our normal line. So this is the equation of the tangent line. This is the equation of the normal line. So here you can see that I've gone ahead and graphed this for a specific point. So here, the red curve is our actual function. Here, this curve is our tangent line, and you can see that's believable, right? And then that's our normal line. So that's just our tangent line, and then our normal line is just perpendicular to that. And again, though they're currently in slope-intercept form, we could easily put them in point-slope form and just tweak the slope to make it the negative reciprocal. In fact, if your teacher lets you leave it in that form, that's the easiest. So there we go. That's that. Now, one other thing I want to show here. So actually, let me back up. In other words, this makes sense. So our answers make sense. These really are. They do really look like they are the tangent line and the normal line. And again, you can imagine if I tweak these at all. So if I even tweak this a little bit, if I made this 5, now it's completely off the line. So that's how we know that these are real. Now if I get rid of these, so now all I'm doing is showing the tangent line. If I move this basically horizontally, you can see that this is automatically creating the tangent line no matter where I move it to. And again, it's automatically adjusting. So it's like programmed behind the scenes. Now, I don't want to go into too much detail about how this works, but one thing I would like to point out is that if I come down here and I show the actual calculations for how that's working, actually, that's not what we need. Right here, actually, sorry. If you pay attention to this, hopefully it's clear that this is actually the same thing we just talked about. In other words, the way this animation is actually programming this and actually automatically updating as I drag the slider around is that it's using point slope form just like we did to solve this problem. Take the derivative of the function, evaluate it at a, remember, is the x-coordinate of our point of tangency right here. So do that, multiply by x minus a is like x0 in the example that I used, and then I basically add y of 0 right here. That's basically the y-coordinate of the point of tangency. And you can see that if I just program it like that, it will automatically create the tangent line no matter where I move it. So this is how this animation is actually working behind the scenes. It's using the same equation that we used to solve this problem by hand. And this is, in general, the way you can find the equation of the tangent line. So hopefully that makes sense. If you want to pick up this Desmos animation, be sure to check the link in the description. But other than that, good luck, and I will see you next time.